Hello, everyone. This is another exciting episode, IITT, and I think it's the 23rd or 24th one. So we covered more than half of the technical committees this time, probably the most exciting one, but don't tell the others, about earthquake engineering. I'm now in Beirut, Lebanon. It is an earthquake country. I felt a 4.5 earthquake, and I can't wait to feel what the speakers are going to tell me about engineering, geotechnical engineering regarding earthquakes and its problems. TC203. I would like to introduce our speakers, so I will share my screen. So today we have four distinguished speakers. We have Sebastiano Foti, professor from the Politecnico di Torino in Italy. He is a vice chair of TC203, so he will tell us about the technical committee. We have Thaleia Travasarou, leading Fugro in USA and globally. And she will tell us state of practice over 20 years and a case study. Brendon Bradley, professor from the University of Canterbury in New Zealand, also TC203 member. And from the young teams, what happened? Yes, Francis. Francis, you are in beautiful the Philippines, University of Philippines, Diliman, uh, graduate student. We can't wait to hear from you also. So I will give the floor now to the first speaker. Sebastiano, you're ready to share your screen? Thank you for joining us, all of you.
Thank you, Mark. I'm going to share my screen.
I will mute my mic and remember it's interactive, so feel free to interact with the speaker whenever you see that there is a need for our viewer, and I'll do the same. For now, I'll mute. Go ahead, Sebastian.
Thank you, Mark. So what I will cover during the presentation is basically an introduction of TC203 that is related to geotechnical earthquake engineering and related problems, and then a couple of topics that I would like to cover to introduce multi-risk analysis that are getting more and more important, and very often the seismic aspect is a very important one in this context. And I will discuss a bit about open data and the opportunities that sharing the data with the community give to the world community in terms of advancement in the research. And finally, just a few hints about hot topics and what we have ahead of us in the future. So about TC203, TC203 was established in 1985, just after the 11th International Conference, Soil Mechanics Foundation Engineering in San Francisco. At that time, say that basically the time was right for starting this, considering that there was quite thrilling activity about earthquakes in the end of the 60s and in the 70s. And nowadays, TC203 has 116 members, and as you see, it covers basically the world with a good coverage, especially obviously in the region that are most affected by earthquakes, in which earthquakes are an important aspect. This is the composition of the say of the leading group currently of TC203. The chair is John Bray, University of Berkeley in the United States. And then Ada Athanasopoulos Zekos is the secretary, and this is the board that is composed by 4 nominated members. Here you find also the link to our website within ISSMGE website, and you can access also through the QR code. TC203 has organized quite a large number of specialty conferences. Basically, especially, we organized two series of conferences. One is the series of international conferences on earthquake geotechnical engineering. It started in 1995 in Japan, and the last edition was again in Japan, in Osaka, May of the last year. The second series of conference, basically they alternate every 2 years, one under the other, and is the series on performance-based design and earthquake geotechnical engineering. And this, I mean, the need for this conference was pushed by the need for going towards optimal design of the structures. And especially the next one is expected to be in Puerto Varas in Chile in November 2026. And obviously we expect all of you at that conference, and here you can find the link again.
I just came back from Chile. It was
yes,
a Pan American
obviously,
conference. I don't know if
Chile is one of the countries. Basically, in Chile, it was the largest in terms of magnitude the earthquake recorded till now. So this is important for us to come back there.
And Taormina, I saw in your list, Taormina, one of the most beautiful places on earth.
Yes, in Taormina we had the conference in 2012. It was quite successful conference. Obviously,
Beautiful
the setting
place,
helped in having a lot of people over there. One of the things that you can find in the website of TC203 is say the time shot, a view on the past. That is basically what you can find within the time capsule project of the whole ISSMGE. This is a project that focuses on what we want to live for the coming years. And this is, for example, pictures that comes from our website over there. And we call us that earthquakes, unfortunately, are the living labs, and we have to make our best to learn from these fatalities, because it's something that we due to the casualties and to the people, in order to prevent this again in the future. And here you can see the evolution in time of the most important earthquakes and what we learned from every one of these earthquakes. I will cover a couple of examples. One is the two earthquakes that happened in 1964, that are Alaska and Niigata earthquakes, and followed by the San Fernando earthquake in 1971. And I'm calling this because these are the earthquakes that pointed out the importance of liquefaction. Obviously, we know about liquefaction. We have documentation that goes back, for example, to the Calabria earthquake end of the 18th century. But these two are very important earthquakes because, as you see, this is maybe the most famous picture about geotechnical earthquake engineering: collapse of apartment buildings in Niigata, basically a failure due to the liquefaction just below the building. You see, this is basically, it is truly a geotechnical failure. As you see, the structure is absolutely untouched, is a rigid rotation, and is iconic for the damage that liquefaction can make. And the other iconic one is San Fernando, 1971, in which liquefaction caused the collapse of the dam. And again, this called the attention of the community on this topic. The other one that I'm touching is the Michoacan earthquake in Mexico. And this is particularly important because it is the most, I would say, iconic example of the site amplification. Indeed, if you look at this picture, the earthquake was basically along the coast, the epicenter was along the coast of the Pacific in Mexico. But then what happened is that as we moved towards Mexico City, the shaking was much larger than it was at epicenter, and we are 400 kilometers away. So obviously there is something going on over there. What's going on is site amplification. This is a section of the basin of Mexico City that is quite a peculiar material, I have to say, because it's a clay of volcanic origin, and there's a very peculiar behavior. You see over here the response spectrum at different position along this section, and you see that the stratigraphy is quite peculiar, as it is very, very soft materials. Shear wave velocity 75 is really soft material, and below we have some cemented, compacted sand and gravels that act as a bedrock. And if you apply just the very straightforward theory of site amplification, you find exactly this peak of amplification that we recorded in Mexico City. This called our attention specifically to the importance of site characterization, and indeed here the most relevant aspect is the amplification that is due to the thickness and shear wave velocity of this stratum, the importance of site characterization. This is something on which the community has stressed a lot in the past years. Just to provide an example, the need for good quality in geophysical test is something that is very important for our community. This is, for example, a set of guidelines that we wrote a few years ago about the good practice in surface wave analysis. So SASW, MSW, and so far so on. So the analysis of Rayleigh waves for site characterization.
Sebastiano?
Yes, sure.
Sorry to interrupt, just for the viewers and for me. What you're saying is you can have more damage away from the epicenter because of the soil layering, right?
Yes. And
so we can say that the energy is transmitted, but then it has either high frequency or high amplitude, and in soft soil it becomes high amplitude.
The thing is that the energy is traveling toward the system, then is getting trapped in this low velocity layer, and what happens is that we go basically to resonance. So we go to resonance for the layer, and this means that you amplify some specific frequencies you pointed out. So for example, if we go back on the recordings, you see that the recording in Mexico City is almost an harmonic signal, because we amplified exactly that frequency that is consistent with the frequency that we can estimate from theory.
And this specific depth, it became resonant. Yes.
And so this is consistent also with the damage that was observed in Mexico City.
20 floor buildings, yes. And in rock, if you have a rocky area, it's less.
In rocky area, we do not expect a stratigraphic amplification. Obviously, we still can have topographic amplification if the topography is such that energy is focusing towards the top of the hill.
Thank you.
So I was saying that one side is the importance of the shear wave velocity. The other side is of the medal is the behavior of the material at different level of strengths. And so going back to Mexico City case study, basically, if we look at the behavior of the material, you see that this is very peculiar. It's outside all the range of all the other materials. And indeed, if we consider this clay is a very peculiar clay, we have that the plasticity index is about 300. We have a very large structure of this clay. And again, this call the attention on the other side, on the laboratory testing. We are going to be back on this in a few minutes. So I was saying that I'm going to cover two aspects to give just a snapshot of say hot topics nowadays. One is multi-hazard analysis. If we consider multi-hazard, we can have different situations considering hazards that overlap in time or in space. You can find the details in these slides. I will present you an example of what happened when we have a spatial overlap. So maybe the obviously the two hazards are not at the same time, but they act at the same location. And the example I'm going to cover is the interaction between local scour around the foundation and earthquakes. Indeed, if we have local scour, we expect a different behavior of the structure. Very often, this is not remediated in time, or at least the mitigation of scour takes some times and some money, considering the number of bridges worldwide. It's not easy to have resources to repair all the bridges in this respect. So this has an impact on the behavior of the bridge, and also an impact with respect to what is going to happen in coming earthquakes. Nowadays, this is covered with some level of details. I'm going to present an example of how we can investigate this aspect. And this example is based on a set of physical tests and then numerical analysis that we run in cooperation with ATH Zurich. So these are centrifuge tests. This is the model. And this is the way in which we tried to simulate the whole process. In 1G, simulated the scour, detected the scour with a 3D scan, reproduced the scour with a 3D printer, and then running the centrifuge test. This is an example of results that point out the different behavior of the say unscoured foundation against the scoured foundation. Obviously, this large difference that we observe over here in terms of behavior of the foundation has a very strong impact on the foundation. Remember also that this also implies the fact that we are changing the frequency of the structure, so the structure is going to be quite different in terms of its dynamic and specifically seismic response. The second aspect I would like to cover is the importance of open data. This is something that is increasing its importance nowadays, especially because nowadays we have tools to share data. These are examples of the database worldwide, and these are some hints about best practice for moving forward. We have to go more and more towards relational databases, and we need the databases that remain in time, so we remain accessible in time. So it is important to associate REDOI and so on. One example is the next generation liquefaction. So we basically are going from the format of the past, that is the format of a simple spreadsheet, to a relational database, in which we can really use the data, considering their location, their characteristic, and each one of these points basically has all the information attached in a geographic information system. So this is a big step forward we did in the past years, and this is an opportunity for researchers to share data and to use this amount of data for possible application. We will see something in a few minutes, and here you can see the increasing of data in the next generation liquefaction database, and so we are moving towards the possibility of having an amount of data that can be used, for example, for training artificial intelligence. These are a couple of examples that we developed in Italy, a database of laboratory tests. So again, the importance of the cyclic and dynamic behavior of soils, and you can access it, open access to the link before. And this is another example, is the database of surface wave test all around Italy. In this case, we use this database, again, is freely accessible, is published as an open access. And for example, we use it for training a new geostatistical model that can reproduce the variability that we expect in shear wave velocity. And here you can see a comparison with the Toro model, that is a widely adopted model for reproducing the uncertainties, but provides some, say, in some way, an excessive level of uncertainties in some layers. And this is our model that was developed a few years ago. And if we check this model against experimental evidence, for example, this is a case study in Mirandola, Italy, you see that the uncertainty can reproduced by staying close basically to what we observed on site. So I would say this is a reasonable reproduction of the uncertainty, still keeping the signature of the sites under control. So still being compatible to the other information that we have with this, for that site. And finally, I'm going to close with a few hints about current topics that is something, some topics on which I expect research to be very active in the coming years. Obviously, in this time, it is quite obvious to start with artificial intelligence. Here you can see some application. I'm not going to cover all of these applications, but here you see application about induced lateral spreading, prediction of BS30, interpretation of CPT, and analysis of granular flows. One important aspect is that to train artificial intelligence, we need a large amount of data. So this is, again, the importance of open access data. The other important aspect is that obviously these tools, are something about we still need a lot of research to bring them from the research to the practice. So I expect this to happen in the coming years. Another very important aspect is soil structure interaction. And nowadays we are recognizing more and more the influence of the soil structure interaction on the behavior of the structure infrastructure, like bridges, for example, in these examples. And this is very important. As we were talking before about Mexico earthquake, and the soil can significantly alter the input signature, but not only, also significantly alters the behavior of the structure. So if we compare behavior of the structure as if it is a fixed base, and if we consider actually the interaction with the soil, we have completely different behaviors. These are examples of what we can do nowadays with advanced analysis. And a new frontier, I think, that is going to have more and more importance in the coming year is the coupling between physical and numerical modeling. So nowadays we are going towards simulation that are hybrid in the sense that we couple the numerical response with the physical response that can be observed directly in the lab. So this is another topic to keep our eyes on. Finally, in terms of new frontiers, bio-inspired and bio-mediated geotechnics is keeping a larger importance. We try to look at the response of the natural system and to learn natural systems as they work. Here you can find some examples. For example, if we consider root-inspired anchorage system, considering the behavior of roots, we can try to think about new possible solution for our engineering application. I mean, this is a new topic, but at the same time, it's something that is well rooted in geotechnical engineering. Indeed, this is an example of the restoration and preservation of the Burano Bell Tower in Italy. So we are back in 1985, and you see what at that time people were calling exactly root piles. So a network of piles to keep the bell tower safe. In terms of geotechnical earthquake engineering, this has a strong effect, for example, for liquefaction mitigation, where biocemented biocementation in loose sand can strongly improve the response with respect to liquefaction. And in this case, it is monitored in terms of increase of the shear wave velocity. Obviously, as we increase cementation, we increase the shear wave velocity, but we also increase the resistance to against liquefaction. So again, I expect this to be more and more important in the coming years. And with this, I would close my talk. So thank you very much for your attention. And
Thank you, Sebastiano. Thank you so much.
thank
Very
you.
nice summary of what we're doing in earthquake geotechnics. Talia, the floor is yours.
Great. Can you see my screen?
Yes, perfect.
All right. So thank you, Sebastiano, for this very insightful talk, and thank you for the invitation to present. And as a background to my presentation, last year I was invited and I had presented as part of the 150-year celebration of the Journal of Geotechnical and Environmental Engineering. And at the time, I had presented on the evolution of the field of geotechnical earthquake engineering through publications in that journal. So that would be probably the state of the art, how we're calling it. And so for this presentation, I thought it would be interesting to look at the evolution of the state of engineering practice and illustrate that evolution over the past 20 years, where I have been practicing approximately, through one project case study, where the interesting thing is that we performed the initial assessments in the early 2000s, and then the owner asked that we revisit and we update our evaluations 20 years later. So it's sort of an interesting case study.
You should publish on the HTC website. You know, ISSMGE has a new heritage time capsule website. So it would
well,
be
I just
great.
thought of the topic from your
Amazing.
kind invitation. So yes, maybe
I
I'll
can't wait.
publish it eventually. For now, it will
Go ahead.
stay exclusive in this interactive technical talks. So with that, and as a starter, what I had presented last year as part of the AACE 150 year celebration of the journal, that we can generally subdivide the field of geotechnical earthquake engineering in 4 main topics. And these, by the way, exclude the seismic hazard analysis and the development of design time histories that also Brendon will be discussing. And they are more, at the interface of engineering and seismology. So when we're looking at engineering, 4 broad topics, one to the right, the site response analysis and local site effects, to come up with near surface ground shaking. And this requires methods to propagate ground motions from competent soils at depth to near the surface. The second is the seismic analysis and design of earth and retaining structures. And traditionally here, we're also looking at seismically induced slope displacements. The third would be the seismic design of foundations and soil structure interaction. And here, traditionally, geotechnical engineers come up with spring and dashboards or perform coupled analysis with finite elements and finite differences. And the fourth is the very wide and broad topic of soil liquefaction that can also be subdivided into subtopics that include the liquefaction triggering hazard, evaluation of liquefaction effects and associated demands, and mitigation. There are also some areas that can be viewed as enablers, and progress in these areas triggers significant advancements in our main topics, including adoption in practice. And this is not a comprehensive list, but it includes the characterization of dynamic soil properties, availability and ability to perform physical model testing that allows for calibration and validation, numerical modeling platforms, and the availability and incorporation into assessments of probabilistic and stochastic approaches. And so with that, and I thank again Sebastiano for coming before me and discussing in the time capsule initiative for TC203. But as part of that initiative, this initiative summarized the evolution in the field of geotechnical earthquake engineering in terms of three overarching periods. The first back in the 60s and 70s, which was the period of raising awareness, 80s and 90s, the period of developing early models and methodologies to assess earthquake effects. And then for the past 20 years or so, where I have been mostly practicing, we have been really looking at the refinements of these models and methodologies, but also are developing more advanced models and tools for more advanced evaluations. So now with that as a background, how has the state of engineering practice followed this evolution in our field? And I want to give an example through a project that I have worked on. I started 20 years ago, worked on the initial evaluations, and then a couple of years ago, pretty much performed or revisited those evaluations. So let's look at that. So this project is an immersed tube tunnel, approximately 5.5 kilometers in the San Francisco Bay Area in California. And the tunnel was built back in the 1960s, where there was limited understanding of the elevated seismic hazard in the area. It is located within 15 kilometers of two major faults that are capable of magnitude 7 to 8 earthquakes. And so now, because the tunnel back in the early 2000s was approaching its design life, the owner was looking to assess its seismic vulnerability and potentially retrofit. So looking at the alignment here, the subsurface conditions are quite variable in terms of the soil types encountered around the tunnel, the overburden, the thickness of key units, the depth to rock. And what are the key seismic hazards affecting the tunnel? And we can see that these are related to three of the topics that we identified within the field of geotechnical earthquake engineering. So first, the differential site response due to the variable conditions along the tunnel, and this would cause axial transient demands, compression and tension in the tunnel. Slope instability, where the tunnel was crossing slopes, and then the associated seismically induced permanent displacements would create residual axial and potentially transverse demands on the tunnel, depending on the orientation of the alignment to the slope. And then soil liquefaction and associated liquefaction-induced demands. Mainly here, we were concerned about the tunnel uplift. So because of the seismic hazard in the area, generally here, when we're using overly simplified approaches, we may end up with very conservative engineering and sometimes too expensive or not feasible solutions. So the owner here was very interested in using the latest tools at any given time during the evaluations to have as realistic an assessment as possible of the seismic vulnerability of this structure. So first, me and my team worked on this project in the mid-2000s and performed the initial evaluations. And then a couple of years ago, so in 2021, the owner wanted to reassess the vulnerability with the latest methods available. So let's look at what were the evaluations that we performed 20 years ago and now how do these look. So starting with site response analysis and differential site response. So when we were defining the methodology at the time to use for assessing the differential site response along the tunnel, we concluded that although there were nonlinear tools that were available at the time, for example, through softwares like DMOD or DESRA, nonlinear site response analysis was not routinely performed, and selecting such a tool as our baseline tool probably would have had a hard time during a review process. So at the time, we opted to perform one-dimensional equivalent linear analysis in the frequency domain, and that was a tool that had been widely used and accepted in practice. And so we ended up performing independent one-dimensional analysis, site response analysis on independent 1D soil columns approximately every 100 meters, and computing displacement time histories at the tunnel level, computing differential displacement every 100 meters, where we had the joints in the tunnel, and these would represent free field strains that would impart compression and extension demands, axial demands.
Talia, I'm
Yes.
looking at the profile and trying to guess where is the water surface.
The water surface is approximately here, and on
Yes.
purpose here I have eliminated, I want to mostly talk conceptual. I don't want to discuss dimensions here because it's also sensitive information, but the water surface is approximately here. So maybe we have 15, 20 meters of water.
It's crossing an island though, right? The tube?
And it's crossing in front of an island, which is
in front. Okay.
and correct. So Yerba Buena Island. And there, actually, you're touching on a point that I was not going to present on, where there is scour behind the island and around the tunnel, and there was an area of slope instability and additional demands, but I was not going to touch on that for this.
And then,
Let's not touch that.
and then also that one is one of the most famous cases of site amplification, because we have a Yerba Buena Island is a rock outcrop, and just close to it there is Treasure Island that is reclaimed land. So
exactly.
different level of acceleration over there are very important.
Exactly, yes. So here, again, initially, right, our primarily tool 20 years ago was equivalent linear analysis in the frequency domain and independent 1D analysis, right, for differential demands. And what did we do? How did this approach change, a couple of years ago when we revisited this problem? By then, nonlinear analyses were more routinely used. And one main reason is that some of the limitations associated with the overdamping around the Masing criterion have been addressed through improved hysteretic models. So then when we perform this analysis again, we used nonlinear site response analysis in the time domain, but again stuck with the 1D columns. And here we see that when we're looking at the equivalent linear analysis shown with black, that the analysis sort of tend to over-amplify the ground motion near the fundamental period of the soil column. And this is analysis shown for 2 consecutive joints. And if we're looking at the differential displacement time histories, again, black is significantly bigger differential displacement than the colored line. So color corresponding to nonlinear analysis and the black corresponding to equivalent linear. So here, the axial demands reduced by just adopting, nonlinear approaches 20 years later. However, we also recognize that at least, in some of the areas, there was 2-dimensional conditions because of the sloping mudline and sloping rock. And so we also perform 2-dimensional analysis, which are also more accessible nowadays to incorporate these effects of topography and variable stratigraphy in our results. And also these analyses have a better representation of the continuity of the ground along the tunnel compared to the assumption of isolated columns. And so here to the right, we look at essentially the peak displacement between equivalent linear 1D approaches, nonlinear 1D approaches, and 2-dimensional shown with green. And we see that overall 2-dimensional analysis further reduce the differential demands. And then I would argue, so then we went one step further. We looked at incorporating spatial correlation in the shear wave velocity in our 2D analysis. So here I'm showing an example at the top of the spatially uniform shear wave velocity, VS1, and an instance of spatial correlated VS1. And overall here we saw similar results but this is not really something that is traditionally used now in the state of practice. I would dare to say, is it probably still a state of the art? Probably because in order to look at and model spatial correlation, you also need to do many or an increased number of evaluations. So increases the time that is needed to perform analysis. So looking now at the seismic slope stability and the associated seismically induced displacements, to the west of the tunnel, where it crossed the shoreline, the ground was sloping, and the tunnel is surrounded by soft young bay mud. And so the key question was the seismic joint, which essentially was between that transition structure and the immersed tunnel, appropriately designed to accommodate residual displacement, seismically induced? And so back in the early 2000s or mid 2000s, we approached this problem with a decoupled analysis approach. And this is a three-step type of evaluation, starting with performing pseudostatic limit equilibrium analysis to calculate the yield acceleration, and then followed by two-dimensional total stress analysis to compute a horizontal equivalent time history, which is representative of the sliding mass. And at the time, we're using software like Quad4M. And then you would integrate the seismic, the horizontal equivalent acceleration time history through a Newmark type integration to calculate seismically induced displacements and generate graphs like this showing the estimated displacement as a function of the yield acceleration. So for this case, for the mean of all the ground motions, we would estimate approximately 7 inches in this particular case of downward slope movement. So these analyses, we know now that they have significant limitations. For example, we calculate just one displacement, which is an index of the overall slope performance, but we're not able to calculate the deformations across, the moving mass. And also KY is calculated based on one value of the undrained shear strength, if you will, and doesn't recognize a potential strain softening or evolution of slope strength with time. So when we revisited this analysis a couple of years ago, our main tool became fully coupled nonlinear deformation analysis, time history analysis with improved constitutive models, effective stress, bounding surface plasticity models, which also can reasonably capture cyclic softening behaviors. And so these fully coupled analyses now provide an improved understanding of the behavior of the entire slope system. And here, for example, we see we can calculate different displacement as the slope changes above the tunnel, and overall we have a more realistic representation of the behavior, including incorporating strain softening behaviors for this soft clay. And finally, let's look at the assessment of soil liquefaction and liquefaction-induced demands. In this particular case, we're mostly interested at tunnel uplift. And so looking at the typical cross-section, the immersed tunnel was built in a trench, which was excavated into the native soils and filled with sands and gravels that can liquefy during strong shaking. So to assess the tunnel's vulnerability to uplift due to liquefaction of the surrounding soils, a range of approaches was adopted throughout the project, from more simplified in the beginning to more advanced later on. So we first, in the very beginning, we approached the liquefaction-induced uplift problem with a force-based methodology. So this essentially involves first performing simplified liquefaction triggering assessment using established empirical methods, and then based on the factor of safety against liquefaction calculate the uplift force, compare this to an available resistance, and calculate a factor of safety against uplift. So in this particular case, we're coming up with very low factors of safety, and this suggests that mitigation liquefaction mitigation, in this case through, for example, stone columns, was needed to mitigate for the tunnel against liquefaction-induced and seismically induced demands. However, was that necessary? Was ground improvement really necessary? So we quickly refined our approach at the time using a deformation-based framework. And so the main question was here, would it be possible that the tunnel displacements and overall demands that are induced by liquefaction could be small enough or tolerable despite the fact that the soil liquefies? And so for that, we performed a series of two-dimensional nonlinear time history, soil structure interaction analysis. At the time, there were limited constitutive models for liquefaction, but we adopted one for these analyses. And we also performed two project-specific centrifuge tests at the University of California, Davis, to allow us to provide insight into the uplift mechanisms and allow us to calibrate and validate our analysis tools. We even performed simplified three-dimensional simulations, and these are simplified because they are three-dimensional on one hand, but the constitutive model, it is essentially a more Coulomb type total stress model that has been appropriately calibrated. However, through these types of evaluations, both numerical and through model testing, we were able to demonstrate that despite soil liquefaction, the tunnel could tolerate liquefaction-induced demands, and hence ground improvement for liquefaction mitigation was not needed. And these analyses at the time, in mid-2000s, were considered state-of-the-art. I would argue that this type of evaluations now would be more considered state of practice, especially considering the availability of more advanced constitutive models that are implemented in commercial software platforms that are available to practicing engineers. When now we revisited this problem a couple of years ago, one question that the owner asked was whether our previous analyses, the two-dimensional analysis mostly, were adequately capturing the seismic demands given the three-dimensional nature of the problem. We had axial demands, tunnel transverse demands, uplift demands in the vertical direction, three-dimensional bathymetry and stratigraphy. So were the 2D analysis appropriate? And so we recently performed fully coupled three-dimensional soil structure interaction evaluations, mainly for verification purposes. And this was essentially to identify any fatal flows leading to erroneous conclusions previously. And so I would argue that at this point, these types of evaluations are still limited today, primarily because it takes significant effort to calibrate and validate each component of a complex model. And I see that we're maybe quite a ways from these evaluations to become a state of practice. Probably they're still going to be used mainly as a verification tool, at least in the near term, for more complex projects. So with that, some concluding observations on the evolution of state of geotechnical earthwork engineering practice in the past 20 years. There have been significant advancements. We have mostly transitioned from purely empirical to also using routinely numerical methods, from decoupled multi-step approaches to fully coupled. We have embraced deformation-based and overall performance-based evaluations rather than force-based designs, and are more comfortable, I believe, using two-dimensional tools instead of one-dimensional when needed. And these advancements have been enabled mostly by improved soil constitutive models that have also been implemented in finite element and finite difference software platforms. But that said, there are so many new developments, right? With artificial intelligence, with new materials, with multidimensional problems, with special soils. And still the state of practice lags somewhat behind those most recent developments. And I think this is an opportunity for practicing engineers. We need to be aware, we need to follow the latest developments and leverage this understanding and these recent developments in the field, and incorporate those into our practice, especially when for the particular problem that we're looking at, more established tools appear to have limitations. So with that, I'll conclude the presentation.
Very nice, Thalia. Very nice, showing this evolution of earthquake geotechnics. I like it.
Thank you.
Brendon, are you ready? They took most of your time, but
yeah. That's
no
okay,
blaming, no blaming.
So
The floor is yours.
Thanks,
New
Marc.
Zealand. Go ahead.
And it's great to be able to follow Sebastiano and Thalia as well, and that I'll try and tease out a few of the sentiments that they mentioned. I hope to some extent that what I'm going to discuss in the next 10 or so minutes, Sebastiano would consider as one of the new frontiers and hot topics, and that it also builds on the same sort of sentiment that Thalia was mentioning, that as we're getting significant improvements in computation, that leads to this sort of positive feedback loop where we can ingest more data, we can try more things, and we're able to iterate faster. So I want to talk about the opportunity of advancing our seismic hazard analysis through ground motion simulations. That was the part in Thalia's second slide, I think it was, where she was sort of saying off to the side, just before the site response, you had the ground motion prediction and seismic hazard analysis as well. So just to make it clear for the listeners, that we're all on the same page. When I talk about ground motion simulation, I'm referring to a situation like this where we actually try and model as a function of time how the rupture evolves over the causative faults, and then what is the consequent wave propagation through the Earth's crust, how it interacts with the near surface materials, and how that ultimately results in a ground motion at the surface that varies as a function of time. And so this is quite different from empirical models, which traditionally just estimate some simple intensity measure of shaking, like peak ground acceleration or peak ground velocity. And it's particularly important in the context of, for example, what Thalia again was showing, where if you're going to do any type of dynamic analysis, you need an estimate of the ground shaking and how it varies with time. And so we have that usual what we call ground motion selection problem, that through these methods to simulate ground motions directly, you actually get the time series of acceleration, and therefore you avoid the problem of having to select a compatible set of ground motions consistent with your seismic hazard. Always when...
Brendon,
yes.
This is an impressive video. So the ground motion was, this simulation was done from data collection or from theoretical predictions?
Yeah, I guess a combination of both, in the sense that, strictly speaking,
Very
we are
nice.
solving the 3D wave equation for like a viscoelastic or nonlinear plastic material. Ultimately, in that regard, it's just a model, but clearly there's a lot of important work and a lot of effort to try and validate those models to make sure that they reflect reality relatively accurately. Naturally, whenever in any given discipline trying to present something new, there's some skepticism that maybe if it's too good to be true, it probably is. But a lot of the time that's quite healthy skepticism and requires us to think about how do we validate these methods and calibrate these methods to make sure that the sort of conceptual potential of them can actually be met in reality. But I think it is important to recognize the sort of trend and the tailwind that exists there. And one analogy that I think is particularly useful is comparing how we do things in this context of earthquake-induced ground motion prediction with how we do things from a weather forecasting perspective. So in the upper half of the slide at the moment is this compare and contrast between, on the left-hand side, the state of practice at the moment, which is empirical ground motion models. So simply put, they use historical observations highlighted by the points that I'm showing, and then they use some form of statistical regression to come up with a median prediction and a distribution around that prediction, which is highlighted with the black lines. They're not purely statistical models in the sense that we often need to extrapolate beyond where we have good constraint in the data, and we would try and intelligently do that extrapolation by having some sort of theoretical understanding of what we expect, but they're largely grounded in directly doing regression on the data. In contrast, on the right-hand side is just a single snapshot similar to that animation that I was just showing before, where in this so-called physics-based context, we're trying to explicitly or directly represent those salient phenomena, the actual rupture, how it evolves with time, the actual wave propagation, how it occurs with time, how you get the sediment amplification, as Sebastiano was showing in cases like Mexico City and so on and so forth. So that's kind of that example in a ground motion context. If we compare that with a weather forecasting context, the analogy would look something like these two diagrams that I'm showing in the bottom half of the image, where starting on the bottom right-hand side, this is just the standard of practice now that we have meteorological models of the atmosphere. We model, changes in air temperature and pressure and precipitation and so on and so forth. We ingest in a largely continuous fashion all of those measurements, and we constantly provide predictions in the scale of, minutes or hours or days or weeks in advance. And clearly we all know from our firsthand experience that as the prediction goes out with time, we have more uncertainties in the model and therefore the poorer the prediction. But it's quite interesting to draw then the parallel with the bottom right-hand image of, what is the equivalent of an empirical weather forecast? Today we are toward the end of February. This slide I made is an old one, so it's got month of May there. But it would be the equivalent of saying the last 100 years on this particular day of the year, this was the 100 values for the daily high of that day. And this was the 100 values over the last 100 years for the daily low. And so my prediction for today's daily high is going to be the average of those last 100 days for the 25th of September. Okay, sorry, 25th of February, excuse me. So in that regard, when you sort of say it that way, it sounds kind of insane to think that we're going to predict tomorrow's weather based on the 100-year average of what tomorrow's weather typically was, rather than use today's weather to try and forecast tomorrow's weather. But that's essentially what we're doing with empirical ground motion models, where we're making use of that historical data. And so although that clearly is not the way we're doing things from a weather forecasting perspective, actually we still make use of that sort of idea of empirical weather data. Whenever we have record high temperatures, we would talk about that relative to that historical norm, right? So we still think about weather in an empirical sense, but when we're actually doing forecasts, we're making use of our physical models. It's not that geotechnical earthquake engineers and engineering seismologists are not as smart as meteorologists. The problem is harder in the sense that we're trying to forecast phenomena that are happening below the surface, where the forecasting is phenomena above the surface. So we can make use of things like satellite imagery as well to have much better data that we use to calibrate those weather forecasting models. But there is also the same trend that forecasting extreme weather is substantially harder than forecasting normal weather, in the same way that we can forecast the sort of average shaking from an earthquake relatively well, but if we're trying to forecast the next specific earthquake or a very large earthquake, we're going to have a lot less data, and that's going to be a little bit harder as well. So then I guess the question is, faced with this proposition from me to you as the audience for, we should do these ground motion simulations more, obvious question would be, well, why is now the right time for us to kind of make that transition? These methods for doing ground motion simulation to some extent have existed for something on the order of about 30 years. And so now, why is now the right time? And I think the rationale for that is largely associated with a transition from using these methods for scientific exploration, for using these methods for actually engineering prediction, where we can estimate the outputs from these models well enough now that they're actually useful in an engineering context. And so three sort of tailwinds that I think motivate why now is the right time. The first one is simply if we look at progress or lack of progress in our prediction of ground motion using the current sort of conventional methods. This slide is an example from a paper in 2009, where on the y-axis is sort of the standard deviation in predicting the model, and on the x-axis is the year that any individual model was published. And you can see some sort of general trend that for about the last 45 years, since something on the order of 1980, there's a lot of scatter between the standard deviations suggested by individual models, but there's not really a clear downward trend. Like, we're not getting drastically better at these predictions, and we still have quite a high standard deviation. This paper, as I mentioned, was published in 2009, and a few examples since that time of major projects again suggest that those standard deviations are not really decreasing. Sebastiano talked about the importance of big data and open data and so on, and the ground motion field is no exception. So here's an illustration of the number of high quality recorded ground motions as a function of year, and we can see that on a log y-axis we basically have a 4.5-fold increase in the number of observations every 10 years. But then if we actually dive into that in more detail and try and understand, what is it? Is that more earthquakes are happening? Probably not. Are we installing more instruments? Are the instruments getting better? When we sort of disaggregate that data and look at number of ground motions, but as a function of the intensity of the ground motions, so you can see there are 3 different values of PGA, or peak ground acceleration, we see that overwhelmingly most of the rapid increase in data is due to very small amplitude ground motions. And so there's that classic challenge of most of the data is for levels of shaking that aren't really problematic for well-engineered structures. And so how do we extrapolate from these small levels of shaking that are of like usefulness, but not particularly the design cases that we consider, up to the large levels of shaking that we ultimately care about. And my argument would be that when we use empirical methods, it's quite difficult for us to do that extrapolation because we're extrapolating without a strong physical basis. Whereas when we use any method that's based on sort of directly representing the physics provides sort of a natural framework for that extrapolation to occur. Of course, the other tailwind is computing. For a long time, in the last sort of decade, there was a notion that, Moore's law itself in terms of transistor density is sort of finishing, but we've clearly seen continued increases in computing power, the most recent trend being, of course, through GPUs, and now we're sort of starting to see another acceleration where we can combine traditional physics-based simulations with machine learning sort of surrogate models as well. So I think it's quite evident to say that the sort of computational scaling that we'll see in the future will continue as well. And so that increase in data and increase in computation allows this sort of virtuous cycle where we can try more things, we can refine the spatial scales of our problems, we can ingest more data, we can predict more often, we can compare those predictions with observations and kind of go round and round an iterative loop to improve our models. And that's leading to that sort of virtuous cycle and better understanding the 3 main components of ground motion prediction, which is 1, the earthquake source, the actual rupture on the fault and how that evolves with time. 2, the wave propagation path, how do seismic waves travel through the Earth's crust and the way in that they reflect and refract and reverberate and so on. And then finally, the site effects, the near surface site response that, again, Sebastiano and Thaleia already talked about. So in the context of the material I'm going to show, there's not enough time to go into detail talking about validation, but just briefly to mention that obviously ensuring that these methods actually predict observations similar to or better than the conventional models clearly is a valuable thing to do to make sure that we can use them confidently in a practicing sense. And there is significant work happening in that place, and the summary is we're starting to see now in many cases that simulation methods are doing as well or sometimes better than conventional methods. In other applications, maybe slightly less so. If, for example, you have a really poor model for the Earth's crust in a particular region, then there's no reason to expect that you'd get good predictions. But once we've demonstrated some benefit from a validation perspective, we can start simulating ground motions for future earthquakes directly and perform seismic hazard analysis in that context. And so here's just a quick illustration of that as an example in New Zealand, where we simulated possible earthquakes on a range of different major fault structures throughout the country, almost 500 different source geometries shown in the upper left. We considered different randomizations for what we expect for each of those. So we moved where the hypercenter would be on the fault, what the slip distribution could be by accounting for that in sort of a Monte Carlo randomization sense. And so we ended up with a little under 12,000 simulated ground motions. And then we combine those with the likelihood of each one of those earthquake sources rupturing to calculate seismic hazard at about 26,000 locations across the country. And then we could produce a sort of contour map in the traditional sense to see seismic hazard over the region. One useful...
Brendon, just a question. Is this only based on simulation, or it is a hybrid with observation? Only simulation?
So the simulations themselves don't directly use observations, but we would simulate historical events and compare prediction and observation and use that comparison to iteratively update, for example, some of the parameters of the simulations, or the crustal model if you have a sedimentary basin, that when you compare with historical events, you find that at a certain location the prediction's quite bad, you might hypothesize.
Is there any room for hybrid approach?
Possibly, but not easily, in the sense that, if it's hybrid, where are the boundary conditions? I mean, probably the one location that the hybrid can be useful is if you have, for example, a downhole array, then you can basically simulate the result to the bottom of the array, and then you can try and use the actual array directly as a seismoscope, so to speak. But there again, it comes back to one of the things Thaleia was mentioning in terms of the trend that we're seeing is, even with things like downhole arrays, we're assuming 1D wave propagation, and increasingly the evidence is sort of showing that in many cases that's probably not a good assumption. And in fact, we may have had 2 decades of work kind of focused on 1D site response because of downhole arrays, when actually it sort of led us astray a little bit from exploring the real sort of 3D behavior that we typically find actually happens. The other thing that's quite useful here is back to the topic of comparing these new simulation methods with conventional empirical methods. We don't actually have to choose one or the other. There's an established sort of approach within seismic hazard analysis that actually can be used in any different problems, and it's associated with a structured way to consider different modeling approaches. It's referred to as logic trees in this particular discipline, but it would allow you to consider multiple alternative models, and then based on your degree of belief that that model is the best of the available alternatives, you would provide some weighting to that model. So if I sort of elaborate on that in a little bit of a conceptual sense, the current way that things are done is we have these N different models at the moment. They are shown here in the sort of traffic light array of colors, but they're all empirical models in nature. And we don't, at least for state of practice applications, we don't make use of simulated models in any sense. In some state-of-the-art applications, they're beginning to be used. In the very near future, and already in some, let's say, safety critical type infrastructure, we'll start to see this transition where we keep the same empirical models, but now maybe rather than collectively them having 100% of the overall logic tree weighting, that number might be reduced, let's say something like 60%. And we start to introduce one or more simulation-based models, and as a function of their validation performance, we would start to provide some non-zero weight for those models. And then at some point in the future, we might end up at the opposite, where we have basically all of the validation weight in the simulation models and essentially zero weight across to the empirical models. So there's this relatively clear sort of double arrow where the simulation weight, or the collective weight given to simulations, is increasing with time, and the total weight given to the empirical models is reducing with time. When talking about that extreme right-hand side, given that we're currently on the extreme left-hand side, it might be quite hard for some people to fathom, particularly sort of practitioners, that we could imagine a situation where we're only using ground motion simulations and we've almost thrown out these empirical models completely. But again, just to emphasize, as noted in the bottom right-hand side, this is basically where we are now with weather forecasting. And at some point, we were on the left-hand side with weather forecasting as well, right? And so in the sort of 1970s and 1980s, that discipline went through the transition that we're now going through as well. So in summary, in the time that I've had, hopefully I've convinced you at least that simulations have the potential to improve the accuracy and precision of ground motion prediction compared with the conventional use of regression or empirical models. And we're seeing that ground motion simulations are increasingly being used in ground motion prediction and seismic hazard, either directly or indirectly. The outcomes from those simulations are improving the empirical models themselves. I sort of touched on the fact that validation is really important to make sure that we're actually realizing the conceptual benefits of these models, and it's not all just sort of smoke and mirrors, that in concept they can do better, but in practice that they don't. So validation is central for that. And then just reiterating the last points I made, that we can use these simulation models in combination with the existing models in a logic tree type weighting format. And so we don't have to sort of jump from one to the other. We can progressively over time increase the weighting on these models as we develop more confidence in their prediction. So with that, thank you very much.
Brendon, beautiful. Thank you so much. Showing the evolution from a different angle. And I need to borrow or steal that video for educational purposes. I really like it. Francis, are you ready?
Yes, I'm going to share my screen now.
Yeah, try
just
to
checking if you
squeak.
can-
We're past the hour, so try to be on time.
Yeah,
Unlike the other speaker.
yeah, I will do my best. So
Okay, Francis,
just checking
go
if
ahead.
you can already see my screen. Final check. Can you see it?
Yes.
For some reason, I have like black zones. I don't know about the others.
Oh,
Are
that's
you?
the percent. That's the presenter's view. Oops. Okay. It's showing the not the full screen. Sorry about that. Are you seeing the full screen or just the PowerPoint?
Yes, now we see the full screen.
The full screen?
Yeah, we can see the full screen, but for some reason, I have like small gray rectangles covering. I don't know if it's me
No, I can see
or
the same thing.
everyone else.
I can see that too.
I think it's the features of Zoom, but
Mm.
it would better move everything away from one of the screen and
Do that again. Are you seeing the full screen now?
Yeah, the problem is still there, but don't worry about it. Let's keep going.
Okay. So, going for this session, I'm going
You read
to
some more,
share with
yeah.
you
Read
the 1990 Luzon earthquake that happened 35 years before, and how the evolution of engineering practice in the case of the Philippines. So for the 1990 Luzon earthquake, I wasn't even born. So just for a brief background, the regional seismotectonics of the Philippines. So the Philippines is basically sandwiched between the convergence of the Eurasian plate and the Philippine Sea plate. And the convergence is somewhat oblique. So there's a net shear. So right in the middle, there's a strike slip fault zone called the Philippine Fault Zone running basically across the entire Philippines. And in July 16 of 1990, this fault zone ruptured with a magnitude of 7.8 or 7.7 in the moment magnitude scale. So that's one of the largest crustal earthquake in recorded history in the Philippines. So this earthquake is particularly interesting because it's actually hit the relatively developed cities at the time, which is one of those is Baguio City. So you may have heard of that because that's one of the famous tourist destinations in the Philippines because it's one of the few places where it's not hot. So a lot of people visit that for the cold temperatures. But in 1990, Baguio City was hit hard. So just for in context, there's no main shock recording, unfortunately, because according to local state agencies, the recording actually went off the chart. So there was no good recording of the main shock. So, however, there are analysis of coda waves from aftershocks. This one is from August 5. So just comparing the locations of the case of two stations, one in a place called the CLS station, relatively near from the epicenter, and then comparing that with the Baguio City, located around 100 kilometers from the epicenter. So as you can see here from the analysis of the coda waves, although the Baguio City experienced relatively less intense shaking compared to the CLS, but 67 seconds after that aftershock event, there's evidence of relative amplification at Baguio City, suggesting that there's ridge amplification, or in geotechnical engineering terminologies called the topographic effect. So there's evidence of that. And also, in addition to Baguio City, there's also this city called Dagupan City, located right here. So it's also one of the places that were hit hard during the 1990 event. And as you can see here, some of the geotechnical damages, there's liquefaction-induced building settlement. So as you can see here, this is a map of of the city proper. So there's this abandoned river channel, and there's a plot here of the building settlements, and a few pictures of the buildings that tilted as a result of the event. So in addition to that, there's also recorded lateral spreading in river banks and bridge abutments. So a lot of Japanese researchers came to Dagupan City. One of those is, as we all know, is Professor Ishihara, actually investigated lateral spreading, and his group plotted this a rough approximation of lateral spreading along this Pantal River, and then comparing the cases of two bridges. This one's called Bagsaysay Bridge along Perez Boulevard, and then Quintos Bridge in along Fernandez Street. So this is where the importance of site-specific investigation was really highlighted, because in Magsaysay Bridge, as you can see here, because of the characteristics of the shallow subsurface, it experienced extensive lateral spreading. Whereas with the Quintos Bridge, it did not collapse, and because for some reason its location is located on a relatively good ground in terms of liquefaction response, so there's not much lateral spreading in the area. So it's also interesting to note that after 1990, I was told that it's actually the start of what's called the board pile revolution in the Philippines. So a lot of European piling companies offer their services there, and a lot of bridges have been built ever since on board piles, because I think this one is just on shallow foundations, shallow footings, and then some of although not documented here, also others have been already been built on driven piles. So why is that? That in Dagupan it experienced a lot of extensive liquefaction damage? Because exploring the geology, so it's actually located in the coastal area, right on the south coast of Lingayen Gulf, and the materials there are wave-dominated deltaic deposits. And zooming in further, actually the activities in Dagupan at the time was mainly farming and fishing. So there's a lot of paddy fields and fish ponds. So these are ingredients for extensive liquefaction damage. So exploring the evolution of engineering practice in the case of the Philippines, because this may be different from places like Lebanon or US or the New Zealand and even Italy. So actually the main driver for seismic design in the Philippines happened in 1968, where this Ruby Tower collapsed as a result of an earthquake in Kasiguran earthquake. And this is a building located right outside the Chinatown in Manila. So it totally collapsed. So this became the driver for the very first national structural code, and then after that, 5 years later, the building code was officially established. And then 1990 Luzon earthquake, the Hyatt Hotel in Baguio City, as I mentioned earlier, also collapsed. So this is one of the most famous hotels at the time. And so there in 1992, there's major revisions in the structural code. And then the Japanese group drafted this 2013 bridge seismic design specifications and eventually for buildings, the National Structural Code of the Philippines. So in addition to the engineering design practice, it's also interesting to compare the case of site characterization, comparing 1990s versus today. So at the time, Professor Ishihara actually have done some SPT and Swedish weight sounding tests. So at the time, it's largely manual testing. And also with regards to the geophysical testing, there's only this Rayleigh wave method that was only done by Japanese researchers as that time. So it's never used in practice or in this industry in the 1990s. So this became the precursor, actually, if I'm not mistaken, with the modern microtremor array methods. And comparing that with the case today, there's actually a lot of methods that you can use to characterize your site. So a lot of these methods listed here already being done in the case of the Philippines. And I want to highlight specifically what's done in our group. So this is our group doing suspension logging right in the middle of a busy street in Manila for a subway project. And then this one is for an offshore project, so where we actually set up right on a barge for an offshore project. So since TC203 is also heading the performance-based design in geotechnical engineering, I want to briefly highlight this. So we follow the performance-based earthquake engineering framework. So starting from the earth sciences part, from the fault rupture, we combine a lot of data sources from the mining sector, from the open source community through GEM, and as well as our local science agency. And then we characterize the propagation of the seismic waves through recording stations scattered all across the Philippines. And then for the site response component, there's also a lot of studies being done, specifically in this case for Baguio City for microzonation studies. And then this is where the engineering part really comes in. And our technical committee has a wide body of literature for all sorts of analysis, soil structure interaction, system response, and for performance assessment. So let me proceed now for the overview of case histories. I'm going to present 3 specifically, and I will show those that I particularly visited in my brief professional career. So this one is the very first site visit for a post-earthquake reconnaissance I've done in April 2019. So this is a magnitude 6.1 Luzon earthquake. So it was actually felt in Manila. And at the time it was about 5 o'clock. So we're about to go home. But there's a earthquake. So we need to do some inspection after that. So, but for this one, this interesting case of this earthquake. This one is the picture of the Clark International Airport. That this was a former U.S. airbase, but it experienced extensive non-structural damage because the entire ceiling collapsed. So the entire airport has to shut down for a brief time. And then this one is showing the lateral spreading in some rural communities. And then this one is it's called the sand fissuring. And these deposits are actually lahar deposits that was a result of the Mount Pinatubo eruption also in 1990. So another one is our version of the Canterbury earthquake sequence. This was the Cotabato Davao earthquake sequence that happened October of 2019. So a series of magnitude 6 and up earthquakes shook this developed city in Davao City. So an interesting aspect of this earthquake is actually some of the buildings that was designed using performance-based design actually had some controversy because this talk between code prescribed design and PBD because some of the designs of the buildings designed using PBD was actually found to have to deviate with some of the code practices. So that's an actually interesting debate that we can, or discussion that we can have for performance-based design. So lastly, another case history that was in an earthquake in Luzon again in July 2022. So there's also extensive lateral spreading in a coastal community. And one of the highlights of the earthquake is actually it shook this historic city called Vigan. So there's a lot of Spanish style architecture and a lot of old churches that was damaged as a result of the earthquake. And of course, another case of sand fissuring and sand boils. So I'm going to show you also 3 case studies that we're doing as a group for seismic hazard evaluation and analysis of ground response. So for this case, there's this proposed island bridge. So we did some site-specific studies analyzing the site-specific site response. So we've done this same randomization technique that Sebastiano mentioned earlier, for randomization of shear wave velocity profiles. So we've used that to run several site response simulations to develop or modify our site-specific seismic hazard uniform hazard spectrum. And then we utilize that to specify the hazard consistent ground motion time histories for the structural analysis of the bridge. So in addition to that, another case study, what's special here is the coupled liquefaction and site response study we've done for another offshore bridge project in southern Philippines. So similarly, we analyzed the ground response incorporating liquefaction behavior for several hazard levels. And what's special about that is we've also done site-specific liquefaction triggering curve. So as you can see here, a lot of the layers are actually experiencing are actually located on the no liquefaction zone. So showing you here also the excess pore water pressure profile history for a sample time history here. And what's really unique, what's really insightful about this, and we've showed this to the owner, that we explained it to the owner that although liquefaction is triggered at depth, it's also important to consider if it actually manifests through the entire profile. So as you can see here, the time axis is the horizontal axis. Although liquefaction is triggered here because RU is already equal to 1, not all of them, or not all of the damage will manifest right across the profile. So this is where the system response is actually needs to be accounted for in these types of analysis. And lastly, although this is not the focus of our group because this is under the numerical modeling team or numerical modeling technical committee, we also we've done some nonlinear dynamic analysis of tailings dam. So in order to assess the performance and safety of these types of high-risk projects such as tailings dams. So just a few summarizing my part of the talk. So first, major earthquake events like the 1990 Luzon earthquake always bring lessons regardless of what industry you're in, whether you're from the scientific community, engineering, or even for those in charge in disaster response. Second, engineering practices and analysis tools have improved drastically over the years. And third is the performance-based design practice in geotechnical engineering, or for earthquake engineering for that matter. It's important to always evaluate the suitability of code prescriptions, but these types of studies are really advanced and we need to subject it to a thorough peer review process. Fourth is the role of modern technology in site testing, surveys, and documentation, which is particularly helpful in post-earthquake reconnaissance. And lastly, how do we connect all these things to the non-technical people? Because I remember during one of the stories then was in 1990, one of the congressmen actually asked, what are we going to do after this? Do we just move on, or what do we need to improve upon? So I think that's one of the important aspects that we also need to tackle. So as part of the young professionals group, I think it's also important to honor those that honor our mentors and those who took us under their wing. So for my professors in University of the Philippines and as well as my supervisors and principals in AMH Philippines. So just a few seconds to flash the references for the viewers, and thank you very much for listening.
Francis, thank you so much, Francis.
Yeah,
You
thank
are
you.
the future of ISSMGE. Say hi to Mark and Roy on my behalf.
Yeah, I will.
Thank you so much for this these cases, stories, and history. Uh, but what's happening in the Philippines? Thank you all. I don't know if you want to add anything before we conclude. This was really an exciting episode. It's a 23rd one, and we will publish it in a week or two after the team edits it. Um, it's been a pleasure having you on board.
Thank you,
Do you
Mark,
want to
and
add
also
anything, Sebastiano?
I would
Go
like
ahead.
to thank you on the side of TC203 for this opportunity. I think that these interactive talks are a very good way to say show the progress in the different TCs. So it's a very nice initiative. So thank you very much.
Thank you. My hope and my wish is that the future presidents will keep going because we're doing at a rate of one episode every month or two. So I'm hoping to cover all the technical committees. So for the next president, he starts again, and we see the evolution
And we
throughout
see
the
the
years.
evolution,
Yes.
exactly. Are we catching up, with state of the art?
Yes. Thank you so much, all of you. I wish
Bye
you a
bye.
beautiful day
Bye.
wherever you
Bye-bye.
are, or a beautiful
Bye
night.
bye. Thank you.
Bye.
Ciao,
Thank
ciao.
you.